Hi, hello. Welcome to section number 6. Thank you all for being here. So, to start off, just some announcements. First, y'all saw my Canvas announcement about the section and lecture feedback. Sorry we couldn't combine that with the lab one just so that you could do it all at once. The reason why we didn't was because Emma was wanting to send out the lab one the day after the exam. And I said that would not be great. like let's let that settle for a few days. Let's get grades out, and then we'll revisit it after a little while. So please let us know what you think about things and what is and isn't working. We read them actually pretty darn carefully. We go through all of them. And then also I try to incorporate the feedback from that in how I lead the sections for the rest of the term. So if people are we're doing too much practice, then I will do less. If people are we're doing too little practice, I'll do a little bit more. If people are I want less time to work on problems on my own and I want to do more guided, then we'll do that. And I'll kind of go with whatever the group wants as a majority. I will say there are people though that are going to say section the exact opposite things in terms of their preference. And so we have to kind of meet in the middle. But it's also something that suggestions from that have made changes to our course as we go. And so we're trying to make the best thing for y'all to prepare y'all as best we can. And so please let us know if you have ideas. The QR attendance code, we have an alkyl halide. Oh my god, it's matched with the lecture. The other thing is next week I'm doing mid-semester meetings. So I set aside, I think, 13 hours to meet with students, and my plan is to meet with every student in the class. I have set up 10-minute meeting slots. The signups for that are going to go out Friday through Sunday, and it's going to be kind of tiered based on exam scores. So people who scored lower on the exam will get to sign up for slots earlier, just so that there's enough availability. And then as the scores get higher, it'll be sent out a little bit later. In that email, I'll give you a very, very non-official, based on your exam score, this is typically what I've seen students in the past make. It's a pretty wide range, but just to give you some information. And then our 10-minute meetings are going to be pretty quick. So the thing that I would say is come in with a specific goal of what you want to talk about. And a lot of times that goal for most students is either talking about something with exam or certain types of exam questions or talking through their study strategies. One thing that you could do is you could pitch me how you were studying for reactions or planning to study for reactions, and I could tweak that or give advice for it. So really, but also if you're actually I just want to chit chat for 10 minutes, love to chit chat. So the time is yours. But those signups will go out this weekend. I'll be meeting with students next Monday through Wednesday, I think, or Thursday, I forget. Cool, that's most of my announcement things. Do y'all have any logistics before we jump into kind of section proper? Work. So lecture 6 is a little bit different. She's built different. In most of the other reactions lectures, it's kind of you have a ton of reactions and you have longer mechanisms, and lecture 6 is kind of we actually only have 4 mechanisms. They're all really short of 1 or 2 steps. And the hard part is not what is the details of the reaction. The hard part is determining which reaction happens. So it's kind of playing a little bit of a different game. And just so you know, the main way that this appears on exam 2 is the first page of exam 2 will just be a page of box problems that's determining SN1, SN2, E1, E2, and predicting the product. So that's going to be 1/9 of your exam is this. And then some of the ideas from this you'll see from lecture 6 are picked up in lecture 7 with some other reactions. But that's going to be our main challenge today, getting it to where you can decide which reaction is going to happen. So the way that this section is structured is for the first hour or so, we are going to touch base on each of these reaction types of SN1, SN2, E1, and E2. And then we are going to spend the last 30 minutes or so doing practice with that GFP system. Now, at this point, I have seen I would say maybe about 15 universities, how they teach this topic. This topic is typically taught in OChem 1, and it's one of the first sets of reactions that students learn, which I think is horrible because you have to make a lot of decisions. There's stereochemistry involved. Like, it really feels non-intuitive for first reactions. So I kind of like that y'all have seen a little bit more before getting to this. But of all of the universities I've seen, of all the textbooks I've seen teach this GFP system is the one I hate the least. So, like, I don't like any way of teaching it. I don't feel like this is a, like, solved game of, like, how to teach substitution and elimination. But GFP kind of gamifies it in a way and gets you kind of trained for this algorithmic thinking. That is one of the better ways that I have seen to do it. So I quite like it. It does not work 100% of the time, but it, like, primes you for how to think about this. So we will get into all of that with the details. For those that came in, do you want to scan the QR code before I move on? And very briefly, the things I was just saying before is I'm doing one-on-one meetings with students next week. And so the sign-ups for that will be sent out, and then the feedback forms. So, work. I'm also making the executive decision to bring back transition music today. So, to jump into it, let's get our first transition. So SN2. Big strokes. This is substitution reactions. Substitution reactions substitute. Typically, they're substituting a leaving group for some other chemical group that is often a nucleophile. So the mechanism for it, so easy, so simple. Sorry, I did not expect that to be a laugh line. No, it is. So lone pair on the nucleophile does a backside attack, that's kind of how it's referred to, and then you kick off the leaving group. So a lone pair on the nucleophile is going into the sigma star carbon leaving group, and then the nucleophile is in its place, substitution. We call it an SN2 reaction. S because substitution, N because nucleophilic, a nucleophile did this, and then 2 comes from rate laws. So remember, like, kinetics and gen chem, 0th order, 1st order, 2nd order, integrated rate laws. We're not doing all that. Literally, we're mentioning it because that's where the name comes from, and we are not touching it further. But 2nd order, it's depending on the concentration of 2 different molecules for the rate. One molecule is the nucleophile, one is the alkyl halide. So that's kind of where it is. Now, SN2, the mechanism, easy part. The harder parts are 1, figuring out stereochemistry involved with it, and then 2, when it happens. Now, the other disclaimer I have is I really tried my darndest with Pavlovian conditioning for today. It's going to be a little messy. I didn't get as optimized as I want. There is a voice memo of me to myself at 12:30 a.m. last night trying to, like, do a little beat and, like, get it together. It didn't work. I considered rewriting lyrics to a Chappell Roan song. Like, we were really trying to do what we could, but it's just going to be a little messy. So, we'll try it. So the main thing that you should be thinking for SN2 when you're thinking about how it happens is inversion of stereochemistry. So our first Pavlovian conditioning, SN2, inversion of stereochemistry. SN2, inversion of stereochemistry. SN2? Inversion of stereochemistry. Good. So let's talk about what it means. When we do this backside attack, this was the thing with the little, like, magnetic balls thing that, like, Logan did, and, like, the thing just, like, boop, scooted off. When we do the backside attack, we start making a bond with the nucleophile, and we start breaking the bond with the leaving group. And it goes from our fanned groups kind of being out this way to being neutral to then being fanned out this way. So, like, it changes our orientation from being fanned out on the left side here to being fanned out on the right side here. And it's because we go through this tetrahedral intermediate, this trigonal bipyramidal intermediate. Again, that's a little bit, like, much. We can check that we inverted our stereochemistry using our R&S skills from lecture 4. So if we label 1, 2, 3, trace it clockwise, it's R. Over here, our nucleophile, our priority 1, is going to be over here. So 1, 2, 3, now it goes counterclockwise S. So that's kind of where we get our inversion of stereochemistry. Now, a disclaimer. Do you remember the annoying problem from the problem set that was like, they were trying to make the S an enantiomer, but instead made the R an enantiomer? What happened? So there are reactions where once you do the reaction, it's going to reassign the priorities of things. So like this inversion of stereochemistry happens because we assume the leaving group is priority 1, and then we assume that the nucleophile we add is priority 1. But there are cases where depending on our nucleophile and leaving group, that won't be true. Have we ever tested that? No. Have we ever asked a question about that? No. Do I plan to ask a question about that? No, but actually it could be a good question. No. So it's more of an FYI, and this is going to be very much the deep exception for like a thought experiment. This is not the rule. Generally, when you hear SN2, you should think. Thank you. Okay, so practice number 1. 3 parts here. The first part should take all of 5 seconds. It is writing the mechanism for an SN1, or sorry, SN2. My God. And actually, that reminds me of a confusing thing. So, do you remember when we talked about stereochemistry? We talked about like, if it has symmetry, it's achiral. If it's asymmetric, it's chiral. And it's like that opposite thing that like throws a lot of people off. There's another one here. So SN2 is 1 step. Whereas later on you'll see SN1 is 2 steps. Hate it. So just don't let that like throw you. Again, the 2 comes from the rate law.
So can you just associate it as like opposites attract?
Like any kind of inverse or opposite trend, sure. So in the practice 1, first bit, you're going to write the mechanism for SN2, super easy. Second one, you're going to predict the product, but we want to get the right stereochemistry with the inversion. So trying to do that, there are a couple ways to draw it. Try out one, and then I'll talk about it. I also want you to check that you did the inversion of stereochemistry by assigning R and S to both starting materials and product. Third one, I'm giving you a product. You're going to have to think, based on this molecule, what was a good nucleophile that I added? And then also, what was the starting material and like the stereochemistry of it? So I'm going to give you a few minutes to work through that, and I'll play some music, and then we will talk about it. Yeah, no, I feel like PS3 is coddling, but yeah. But then, yeah, if you try to do 15, 15's different. Like, I did 15A, got a C, and then 4 semesters later did PS3 and got an A. And, like, yeah, there's not really a good in between. There's Physics 12. Anyway, SN2. So, our mechanism here, we have OH minus. We do the backside attack. Bada bing, bada bang. So, here we don't have a stereocenter, so really easy, really quick. Yeah.
I'm just confused about how, like, in the box right above, in the previous section about inversion,
Mhm.
like, you did a different, it wasn't like a skeletal structure,
Sure.
but, like, if you were to draw this in skeletal structure.
We're going to get to that in a minute, but
Okay.
there's no stereocenter, so we don't have to do anything.
True.
Yeah, so like this is the easy mode of like no stereocenter, just predicting product. Yeah, like we don't need to think harder. We do need to think a little bit harder for the second one. So now there are kind of 2 ways that we can approach this of drawing the product with the inverted stereochemistry. Option 1 is kind of based on the actual like where the backside attack is happening. So we know backside attack is going to be happening here in the antibonding orbital. So we could draw this molecule and kind of put our SCH3 now coming from this left side, which is going to flip down the methyl and hydrogen, but they are going to stay wedge and dash exactly how they were. They're just now down instead of up. So that's one way that you can do it. Let's check with R and S. So when we do this, this is 1, 2, 3, clockwise, 4 going away, so that's R. Whereas over here, we do it 1, 2, 3, counterclockwise, it's S. Have we successfully inverted stereochemistry? Yes, and we've shown the receipts. Second option for how to draw this, which I honestly is my preferred way, because sometimes it can get hard to think about the 3D space of all of this. It's good to know, but like it's not the fastest. Substitution, think about just putting the thing that you're substituting exactly where the leaving group was. And when you do that, you have to swap the wedge and dash. So the methyl is going to be now on a dash and the hydrogen's on a wedge. And if we check our stereochemistry this way, 1, 2, 3, it's clockwise, but 4 is coming out at us. So now it's opposite day. So now it's going to be S. Mm-hmm.
And you swap it just because we know there's an inversion?
Yes.
Okay.
Like these two are the same molecule that is just written a different way. And we are using RNS to verify that for us because it's sometimes hard to see. Yeah.
So when we're doing the attack, is it fine if they're coming from below?
Yeah. Like, you just need to make sure you're attacking the carbon. But, like, yeah, like, this is kind of how you think about it in space in 3D. But this is a 2D representation that's not always going to be faithful. Yeah. Mm-hmm.
So if the priority, like group number 1 is on a wedge or a dash, what do we do? We just place them.
That's a great question. Then I think you still swap the other 2 groups.
Oh, like
Yeah.
like if they're like this, we just.
So, like, let's say your eye was on a wedge here.
Yeah, that's fine.
And then you had a CH3 over here.
Mm-hmm.
Then in your product, you put the leaving group exactly where it's supposed to be. So you would put the SCH3 still on the wedge, but then you would swap, like, now you would put the methyl here and the hydrogen here.
Perfect.
Yeah, so if you swap any 2 groups on a stereocenter, you make the enantiomer of it. Yeah.
So is this not considered a bulky nucleophile?
No. Yeah, and it's because sulfur, it has a really big electron cloud, not like a bunch of steric stuff. And so the electron cloud makes it better. Yes.
For SN2, because it's like important to know that it's attacking from the back. If you had drawn the arrow like
It doesn't matter. Yeah, and that's what Ahmed's question was. Yeah. So last one over here. What is the part of this molecule that we think was added as a nucleophile that did the substitution? The CN. And we can't just have CN alone. We needed like the negative charge. Okay. Yeah, you could have also done KCN, used any ion. But the one that we don't want to use is just HCN because we want it to have a negative charge to be a good nucleophile. So then we can use whichever method, like inversion goes 2 ways. So you can use the same strategies for going backwards. So I'm going to do the second kind of strategy of just put my leaving group where the CN is. Leaving group, pick your favorite. I'm going to pick bromine. Yeah. And then you're going to swap the wedge and dash. So methyl on the wedge, hydro on the dash. You can check it with doing RNS assignment, but I'll leave that as like an exercise. With that, I'm going to plow ahead. I'm a few minutes behind, but we're going to get through it. So that's kind of the stereochemistry side of it. Let's talk about the how do we determine if SN2 happened kind of thing. So we talked about a lot of factors when we were introducing all of these, but at the end of the day, the one that makes the biggest difference is sterics. So there needs to be a kind of gut response, just like inversion of stereochemistry for SN2, a gut response for SN2 sterics. So can we try like SN2?
Sterics.
SN2?
Sterics.
SN2?
Sterics.
Oh my god, SN2! Work, thank you. And again, in absence of a catchier phrase, we have to vary the delivery, you know? So, sterics, I really like the page in lecture where it showed like the target orbital and it showed like the bulkiness of the groups that block that target orbital. So when you have a CH3, there is very little getting in the way of the nucleophile just doing the backside attack. It's really, really accessible. Same with primary. But then if you try to do a backside attack with a tertiary group, all of these have more hydrogens on it. It's going to take up a lot of space, and it's going to make it nearly impossible to do SN2. And so this is going to be the primary factor that affects if we are good, fair, or poor at SN2, the accessibility of that alpha carbon. Second factor is leaving group ability. This is more here for reference, so I'm not going to talk much about it, like PK things. Yes, again, I'm just mostly putting it here for reference. Nucleophilicity, I'll touch on a little bit. So nucleophilicity, the first time I heard it, I rolled my eyes because I'm like, y'all are making up words again. But I think this idea of like characterizing to what extent something's going to act as a nucleophile is a helpful like scale to have. So like the thing that I think is interesting about nucleophilicity is it's not just about having a high energy donor, like HOMO kind of stuff. Like that is important. But the other factor that's just as important is kinetics. So there is a kind of like accessibility reason of like if you have a really bulky nucleophile, potential nucleophile, if it's super bulky and can't access the electrophilic site, it's not a good nucleophile. So it becomes a poor nucleophile. Like there's this kinetics, like how do molecules fit together, that is also entering into the picture. So I think that's cool. And at this point, I'd like to introduce an iconic figure for our class for this lecture. So this is Miss tert-butoxide. Tert-butoxide is the primary example for our class of a molecule that is a poor nucleophile, but a strong base. So remember when you did like acidity in Gen Chem, y'all were doing Ka, KEQ stuff? That's related to delta G. That's related to thermodynamics of a molecule. Whereas we just said nucleophile or nucleophilicity, that's about kinetics. And so imagine this like scale of nucleophilicity and scale of acidity, basicity as separate scales that oftentimes overlap. So oftentimes if we had like OMe minus, good nucleophile, good base. They do the same thing. But tert-butoxide is kind of cool because it is really good at being a base because in terms of thermodynamics, it's like an OR minus or an OH minus. It's a great base. But in terms of nucleophilicity, it's poor. So it's, I think the only example we teach you that has this, she's going to come back. She's going to do a lot of different things. She's going to mess up trends. And so her energy is BK do crime. She is really out here like just kind of bucking up against what you would expect. You're like, miss me? Like, it just pops up. Like, truly. She also has several aliases that I think are very cute. So this one, Cotboo. Cotboo? Like, and also in terms of, like, structures that, like, are kind of a name. Like, you all have seen my good friend Naomi.
I've never called that.
And if Naomi gets a little tired and she gets a proton, she goes home. Love, love, love. And then this one is a bit of a stretch, but I'm like, T, okay? Or talk. Let's talk about it. Yeah. But again, I think it's important to like single out this reagent as something that like messes up a lot of the trends and patterns. So she's iconic, BK do crime. That's going to be SN2. And I do need to keep moving just to keep us on track, but there will be time for questions in a bit, okay? Work. So let's do a transition. E2. So the E2 reaction, E2, it's an elimination. Now eliminations, what's the T? You're eliminating a leaving group. You're kicking her off. And when you do that, and you're not replacing her with something that you're substituting in, if you're just kicking off the leaving group, you make a double bond. So interesting. Now, there's a kind of nuance here with some like labeling that's a little confusing. So I made a little diagram. I made it this morning at 7 a.m. So in lecture 5, when we talked about imines, we talked about the alpha carbon as being the carbon next door to the CN double bond. And we talked about alpha protonations, alpha deprotonations. Great, love that. So a lot of times people think, okay, next door is over here for the alkyl halide, but that's not how the nomenclature works. In fact, they call the alpha carbon for an alkyl halide the carbon attached to the bromine. And so it's kind of like in the imine version, they think about this whole purple thing as the functional group and then alpha one away. For alkyl halide, they think about just the bromine as the functional group and the alpha is one away. So that comes into play with the mechanism here. So for our mechanism, we go to the alpha beta position, and a base is going to come along and deprotonate the beta position. When that happens, it's going to take its electrons, fold it into a double bond, and then kick off a leaving group. So all of it's having to happen. It's very kind of orchestrated, very precise. When we do that, we kick off a leaving group, we make a double bond. And there's a very specific geometry requirement here of how do we get this actually to happen. It's kind of like princess treatment vibes of like everything has to line up in just the right way, or like the princess and the pea kind of situation. So what we need is we need the sigma CH bond and its electrons to be directly parallel to the sigma star carbon leaving group bond. When they are exactly parallel, it allows the electrons to just slide over when that base comes and deprotonates it, and it makes it just really easy to do this reaction. The other thing that we have to think about is in order for the leaving group to leave, we have to put electrons in the antibond. So we need to make sure that this, our donor, is lined up with that antibond because it's on the same molecule. This kind of like parallel of orbitals, you're going to see this requirement come up more, less so in this class and much more in Chem 27. In Chem 27, there are a lot of biological things where like the active site of molecules are holding things in a very specific position to have overlaps like this happen. So let's talk about like how we name this. If we did a Newman production, we look down here, the leaving group would be directly up and the hydrogen would be directly down. So we would say these two are anti to each other, the beta hydrogen and the leaving group. And then we can also think about these 4 atoms, the 2 carbons and the hydrogen and leaving group. These are all in the same plane, the plane of the page here. So it's periplanar. So in total, we say that the beta hydrogen has to be anti-periplanar to leaving group. So the geometry requirement for E2 is anti-periplanar. So you should be thinking E2, anti-periplanar geometry, E2, periplanar geometry. We're going to do like one of them, okay? So we're going to do E2. Geometry. Let's throw the geometry in there. Yes. Okay. Let's do E2. Anti-periplanar geometry. E2. Early or late on the draw. But last one, a frowny, like E2. Anti-periplanar geometry. Yeah. So, factors affecting E2 reactivity, one of them is just this geometry kind of reality check. So let's see a scenario where E2 is impossible. If we look here, we have our alpha position, we have our beta position. Do we have any beta hydrogens?
No.
No. So if we don't have any beta hydrogens,
No reaction.
no reaction. Exactly. This is our reality check for is like anti-periplanar geometry possible. Then, second factor, the primary thing for E2 is base strength. We said that this is a base coming or removing this hydrogen. So this is where your pKa values that you've memorized are coming back. Like, it's something we will use, like legit, and you'll use it in Chem 27. She comes back. You'll use it in med school. Know your pKa values. Sorry. So We say good bases are OH minus or stronger. So typically negative charges on oxygens, on carbons, or nitrogens. And then we say fair bases are between OH minus and H2O in base strength. So they're kind of somewhere in the middle. That would be like our NH3 or CN minus or a like carboxylate. Our weak bases are water or weaker. So H2O, alcohol, all these neutral things, except for this one because this one is also here. It gets a little complicated. But let me ask another one. So if I said like HCl, rank its base strength, good, fair, or poor? Poor. It's an acid. If I said hydrochloric acid, good, fair, or poor? Poor. Poor. Thank you. Okay. That's the big thing. One warning that I see students mess up every year. Every year. The difference between alcohols and alkoxides. So alcohols are neutral. They're like water. Water you can put on your hands. They're so unreal. You drink it. You're made of it. It is a poor nucleophile in a weak base. It's not very reactive. It's not very good at E2. It's not very good at SN2. Alkoxide, she's OET minus, which is kind of like OH minus, which is a base that will corrode you. She reacts with a lot of stuff. She is a good nucleophile and a strong base. And so that is an important distinction to be able to clock when is it a alcohol versus an alkoxide, because they have very different reactivities. Is that okay?
So,
Work. So, yeah.
Did we go over the figuring out which molecules are good candidates for SN2 reactions, or was that?
Yeah, sterics.
Okay, sterics.
That's the big thing. So continuing on with the E2 stuff. So we have this question of like stereochemistry, regiochemistry. If we look at this molecule, we have our alpha position, we have 2 beta positions. Over here, we have 2 beta hydrogens, and on the right, we have 3 beta hydrogens. So if I knew nothing else, I'd be like, probability. There are 3 on the right, so I would expect more of the alkene formed on the right. But there's this whole dude, Zaitsev, who devoted his whole like postdoc or PhD or something to testing the stability of alkenes. And what he found is that we are looking at alkene substitution here. That means like how many non-hydrogens are on the double bond carbon. And as we start replacing our hydrogens with carbon things, or our R groups, what he saw was the alkenes get more and more stable. So the fewer hydrogens and the more substituted something is for an alkene, the more stable it is. And so, in fact, because of that, even though there are only 2 options for this internal one, the internal are going to be more favored because they each have 2 hydrogens on it, whereas the terminal alkene, the one in the end, has 1, 2, 3 hydrogens. So because of that, this is less stable. And so we see that in terms of the percentages, the terminal is 25%, whereas internal alkanes is 55% of the yield. So we favor the internal, and that's Zaitsev's rule. I say Zaitsev, Logan says Zaitsev. I don't think either of us are going to change how we pronounce it, so pick your teams. And then between trans and cis for the internal, which is more stable? Trans. So we do 41% and then 14%. You don't have to memorize these percentages. This is just like, this is the one from lecture, the example values that I think illustrates the trend. And so to spell it out even more, there are 2 kind of big things that hold true. 1, internal alkenes are more favored than terminal. And 2, trans internal is preferred over cis internal. Now, because this is organic chemistry and there are always exceptions, what if we actually want to make the terminal alkene? We want to subvert Zaitsev's rule. We got to be gay, do crime. So when we use a bulky base, like normally, when we just have a regular base like ethoxide, OET minus, she is going to come in, deprotonate, kick off, you form an internal alkene. Easy. But when you have Kotbu, each of these in our skeletal structure kind of hide the size. Look at how much steric bulk is on this molecule. A lot. And so, if it is trying to grab hydrogens, and it has the option of grabbing these, which is in the middle of the molecule, which has other stuff on the sides, like this is also going to be very big. Bum, bum, bum. Is it going to be easier for it to grab something in the middle or something on the end? On the end. And so it deprotonates at a terminal position. And then we get the terminal alkene, the non-Zaitsev or Hoffman product. And a fun fact is Hoffman, the person who is like credited with this like name for getting the terminal alkenes, he taught one of the organic chemistry professors here at Harvard named Serenia, who many of you will probably have for Chem 27. And she teaches sometimes 17 in the fall. She apparently studied with him. And I was like, what? And it turns out he like taught until his 80s. And so like it was very at the end. But she was like, yeah, I did a class with him. And she just like casually mentioned that sentence. And I said, okay. So that is how we can kind of mess with this and choose to get the terminal alkene if that's what we want. So last thing is E2 on a ring. So this is not covered in many other classes, but we really like it because it makes you combine a lot of skills. So if you are considering doing an E2 reaction on a ring, one thing that you must do is you must draw a chair. And for this exercise, what I would like you to do is take this molecule written on the board, and I want you to draw the two different distinct chair conformers. I want you to draw one version where the bromine is axial up, and one where it's equatorial up. So take a minute and do that in kind of like exam 1 style. The other thing I want you to draw on your chair is I want you to draw in all of the beta hydrogens as well. How'd you do?
This is section 6, right?
Yeah. Are you trying to find the notes?
Yeah, it went from section 5 to section 7, I think. So
Just refresh it. I posted the notes this morning because I was making some changes. So if you refresh it on the app, it should go. My least favorite section in lecture, number 7. It's not because it's bad. I just think it's kind of boring.
Oh.
It's good.
So we have our two chair structures. Now, let's think about that E2. What's our geometry requirement again for E2?
Anti-periplanar.
Thank you. Okay, quick on the draw. If we were doing the little Kahoot quiz, you would have gotten the full
My
points.
name on the screen.
Yeah.
Never happened, so.
So we need anti-periplanar with our beta hydrogens. So look at this version where the bromine is equatorial. Does that look like it's going to be anti-periplanar?
No.
No, we need it like up and down. Does this look anti-periplanar?
No.
No. Does this look anti-periplanar?
No.
No, like it's a little up and down, but it's not anti. And so what you're going to find is if you are trying to do anti-periplanar geometry with like a hydrogen that's in a ring, the leaving group has to be axial. And so does the hydrogen. So like none of these hydrogens, even though they are beta hydrogens, none of them satisfy the anti-periplanar requirement. So we would say that this chair conformer is not E2 reactive. Very interesting.
Because the hydrogens.
You have nothing anti-periplanar or hydrogen between the leaving group. Sorry, that was a weird wording. There's no beta hydrogen and leaving group that is anti-periplanar. Whereas over here, when you have your bromine axial, then we can look next door at beta hydrogens. We have 1, 2, and 3 as beta hydrogens. Which of these is anti-periplanar? 2. So do you see how one's straight up, one's straight down? So this is going to be the only one that can be formed in terms of being E2. So we would say that this conformation is E2 reactive. And so our base, our OET minus, is going to come in and attack here, push in, kick off. And then that's going to make our double bond up here away from our methyl. So notice here, we did not get this. This is the classic you'd see on like an online homework, like, Maria expected to get this product, but instead got this product. What was wrong in Maria's thinking? Well, it ignored this kind of anti-periplanar geometry. But what was Maria thinking about if she wrote this?
The more stable.
Yeah, the more stable, the Zaitsev's rule. So not even the more stable conformation. Like, she was thinking about Zaitsev's rule of this is a more substituted alkene. So if you didn't know about chairs and you were just thinking about this flat, then you'd be like, ah, yes, it's going to form this because it's more substituted. No, it's not, because there's no way to get this hydrogen anti-periplanar. Sorry, this hydrogen or this one anti-periplanar. There's no way. So I'm going to add one more piece of nuance to this. So we now have these labels as E2 reactive or non-E2 reactive for chair conformations. But which of these chair conformers is more stable? Option 1 or 2? 2. Quick on the draw again. Dang. That's totally right. This second chair conformation is more stable because it puts our like bulky groups equatorial. So we have this separate kind of metric here of this is most stable and this is less stable. So in order for this reaction to happen, the molecule is sitting in the most stable conformer most of the time, but it's not E2 reactive. So it has to invest energy to get in this higher energy conformation, and then it can be E2 reactive, and then it can form our product. And so there are like more steps, and do you see how just doing this E2 on a ring, we're having to think about a lot more things. That's why we love it. So there 100% will be an E2 on a ring question on the exam.
We still draw the chairs.
You should, yeah. It's also going to be explored a lot in the problem set and a few challenge problems. So you'll definitely get some practice with it. Work. So I'm going to keep plowing forward with another hard transition. So SN1 and E1. Now, we are doing substitution elimination, but the thing that has changed is how we did it. So both of these reactions with SN1 and E1 proceed through a step that forms a carbocation intermediate. And that's kind of the big thing that's different about her. So imagine you're an atom or a chemical group. You're in this chemical bond and you know, it's not working out. So you said, hey, we gave it a shot. I'm going to take my electrons. I'm going to head out. And sometimes when something leaves, it upsets things. You know, things are very raw, but sometimes it can be positive, you know? Yeah. I also, like, do you all know the TikTok that's like, yeah, probably, where it's like a minor inconvenience, and then it's like someone like leaving the office, and it's playing the, just like exiting, leaving? That's what I think of this step, of the leaving group leaving. She just said, it's been great, and stands up and goes. And it's also something that's a little bit different from what you've seen before. Typically, when someone leaves, they're pushed out. It's a lone pair push. It's drama. This is just like, hey, I'm going to go. So this carbocation is formed. That is the slow step, and it takes a long time for that leaving to happen. But once we have a carbocation, we are reactive. We can do things. So a nucleophile can come in and attack our MTP orbital and we get our SN1 substitution product, or we can deprotonate a beta hydrogen here, fold in, and we get our E1 elimination product. So again, we have the weird reversal of, we have a 1 here, but how many steps is it?
2.
Thank you. And then with this, our rate law, because this is the slow step, it only depends on the concentration of our alkyl halide. We don't depend on the concentration of anything else, so that's why it's a E1, SN1, because of rate. Yeah.
So there's no reagent necessary for SM1 or E1?
There is, that's going to come in here, but this leaving group leaving is the slow part. Yes, so we'll see in a minute.
Thank you.
Work. Okay, so if the leaving group leaving is the slow step, the thing that determines like how favorable these reactions are is really about the carbocation stability. So this is where I be less chemical and I have some metaphors that I think work really well for thinking about hyperconjugation. So one way about thinking about hyperconjugation, and actually, do you remember on problem sets 2 and 3, we just said in some of the problem set like answers that alkyl groups are electron donating, and we did not explain it. Does that seem familiar? I had several one-on-one conversations with people about it in like help room, and they're like, how are we supposed to know that? And you weren't. You were learning it then. This is why. The hyperconjugation is why alkyl groups are electron donating. And I imagine the positive charge on carbon is like a natural disaster, like someone's house burned down. So this is the site of the house burning down. We go next door. Hyperconjugation is a neighbor going, there. It'll be okay. And it's just this really weak stabilizing interaction. And physically kind of what's happening is you can almost think about it as like there's tragedy right here, like needing electrons. I have my electrons and I'm leaning over and saying, there. I'll move my electrons a little bit towards you. It's kind of the flip side of induction. If induction was I'm going to tug the electrons a little bit away from you, hyperconjugation is I'm going to move them a little bit towards you. And it's a really kind of subtle thing, but it can add up. So like one of these little there's, if my house just burned down, not helpful. 3 of the there's, still not great. I don't have a house. But once we start talking about 6, it's like, maybe I'll make it through. And if I'm getting 9 there's, wow, my community is here supporting me. It's going to be okay. And a tertiary carbocation is pretty darn stable. Like, she's reactive, sure, but like this thing can exist. You can find her out in the wild. This, a methyl carbocation, no. That's like what just exploded. Like that's the energy. No, carbocation, tertiary, fine. Primary, also rarely formed. So hyperconjugation is one way that we can stabilize carbocations. So tertiary is going to be a good candidate for carbocation formation. But there's another way that we can stabilize carbocations. That's resonance. Yeah, she's the answer for 80% of the things. So if we have a carbocation next to an alkene, we have a resonance structure here. Positive charge. And so resonance is like, hey, I'm your ride or die. You have a positive charge, I have a positive charge. We're going to spread out this positive charge. Your house is on fire, let me take some of that fire to my house. And then everything's less on fire. So it breaks down a little bit in the metaphor, but it really is like, hey, we are in this together with a positive charge, whereas hyperconjugation is so sorry for you, like next door. We also have specific names for some of these carbocations or these positions relative to double bonds. So the position that's right next to an alkene, we call the allylic position. It's giving ally, I'm here to help, take on some of this. The other position that's notable is next to a benzene ring. We call it the benzylic position. And she's out here with a lot of resonance. She's spreading out that positive charge over like 7 atoms. She's doing okay. The other one that's kind of sneaky is if you have a carbocation adjacent to something with a lone pair. Because your resonance structure here can push in, and suddenly you have complete octets. Yeah, a positive charge oxygen, not great, but better than incomplete octets. So these are going to be very stabilizing. We categorize them in the same good camp as tertiary. Do y'all want more nuance, or do you want to just leave it at that? Just a little bit of nuance. a little bit of nuance. Is a tertiary carbocation, it's actually like crazy stable. Like I can't wrap my head around how stable it is with all the hyperconjugation. And it's actually going to be more stable than the resonance, which is crazy, Again, I don't have a good explanation. This is the nuance. But it's so much easier to be like, resonance is stronger. Resonance will be better, spreading it out. It makes it a lot easier. Hence, that's how I kind of introduced it. But actually, the tertiary carbocation, she's kind of like the gold standard for a carbocation. But y'all don't know that. That's just kind of background. And that's for when you become chemistry majors and you're like unpacking it. Yeah. So for us, think resonance is the strongest you can get.
Wait, sorry.
Mhm.
How is this like important to like the topic? Like,
Yes, that's a great question of like, why do we care about all of this? Why did I go on a detour? It's because the rate determining step for this reaction for SN1E1 happening is a leaving group leaving. And so if we make a stable carbocation, that happens faster. Like if we can form a tertiary carbocation, the leaving group's going to leave a lot faster than if we form a primary carbocation. Yeah, so that's how it kind of relates and comes back. Yeah. I had one other comment here. Y'all are going to be doing funky things with carbocations tomorrow, so she comes back a little bit. But let me just wrap up the last couple topics here with SN1E1. So when you have the carbocation formed, what is the hybridization of this carbon? sp2, because we have an empty p orbital, so she's not hybridized. So what's the geometry of this? Trigonal planar. So she, flat. She's not tetrahedral, things going up and down, flat. With that, our empty p orbital is going to be perpendicular. And so our nucleophile, we could go and attack the top lobe of the empty p orbital, or we could go and attack the bottom lobe. And depending on which one we attack, we're going to get different stereocenters, R or S. So a kind of like hallmark of an SN1 happening is you get a mixture of enantiomers in the product. And the other way is we could write this one way, and to indicate that we get both of them, we could put plus/minus. That just says we have a racemic mixture. Now, this is like the rule, like most of the time, but what if I said about every rule I've mentioned today? Nuance, subtlety, exception, yes. So the nuance, subtlety, exception for all of this is, imagine I had my leaving group leave, I have my p orbital here, and on the top face, the face that has the wedges, I have these big bulky groups. And on the bottom face, I have hydrogens. Do we think that the nucleophile is going to attack the top face or the bottom face? Bottom, just because it's more accessible. So this is SN1, but we only get one enantiomer as the product. Wait, what? Because on the bottom face, the only things that you're having to contend with are hydrogens down here. So when you approach from below the molecule where the hydrogens are, it's easier to access this carbocation. It's hard to think about this because, like, essentially it would be coming from behind and attacking. Versus coming from this top way, and if these are coming out of the page at you, they're physical barriers to get to the carbocation.
Oh, so the arrows above, like the red and blue arrows for the two ways it could enter, are not like...
For this bottom example, it would be from outside or from inside.
Okay.
Yeah, the kind of flipped perspective there. But again, we don't really ask about this. It's more so like maybe something you'll see on a PSEC question or like fun thought experiment. But generally speaking, SN1, we get a mixture of enantiomers. E1 typically follows Zaitsev's rule. But then we have this kind of interesting thing that up until this point, we've done SN2, E2, and then we lump SN1 and E1 together. And it's because both of them have to form this carbocation. And so typically if you're forming carbocation, either one of these is going to be possible for the second step, SN1 or E1. And so when we're trying to predict what the major product is, we need to figure out who wins. Generally speaking, SN1 wins. And it literally is just because it's faster. It's faster for this nucleophile to bump into the empty p orbital than it is for the princess treatment of this sigma bond to line up with the empty p orbital and like this base to come along too. Like that's more to coordinate in terms of logistics. So SN1 is faster. SN1 wins when you are kind of good for SN1 E1 or when you're tied between them. We can mess with it a little bit. Yeah, trend of the day. So if we wanted to increase the temperature, we can get more E1 product. Some classes do a lot with that. We do not. So generally speaking, if you are ranking for SN1 E1 and you say that that's going to be the reaction type that happens, SN1 is the one that's going to predominate. Given that, we need a way to get E1. To get E1, we conk it. So what we are going to do is with a secondary or tertiary alcohol, we are going to add concentrated H2SO4. Her name, sulfuric acid. So if we are in an acid, we have an alcohol, what do we think our first step's going to be? Protonation, because we're in acid. So we protonate her. Suddenly OH, bad leaving group, becomes OH2+, good leaving group. She is going to leave, make a tertiary carbocation, which is pretty stable. And then all that's left in the beaker is this guy. Now, sulfuric acid, strong or weak? Strong acid, so its conjugate base is? Weak. So in terms of being a base for this reaction, it's not very good. It's a weak base. But she will never act as a nucleophile. And it's because she has a lot of resonance. Like there's some like complicated baggage going on here. And so she just won't act as a nucleophile. It's only a base, even if it's a weak base. So if this is the only thing that can happen, then it will do the thing it's not very good at and just be a weak base. And then we will get the E1 reaction. And in this case, we get only the E1 product because it can't do substitution. So that is our kind of one way that we are getting mostly just E1 product. You'll see some other kind of variations where E1 pops up later, but we haven't talked about it yet. Mm-hmm.
So this is just another way to only get E1 is to not have any.
It's our only way to only get E1.
Oh, because the temperature.
We don't really use, yeah. Like it is a strategy, but like we don't have any problems that do that with y'all, and it's more kind of like an FYI. Some classes go much more into temperature, some classes go much more into solvent effects. We're generally not going to talk much about solvents. If it does show up on an exam question, I will talk about it in the review, so you can deal with it then. And I think solvents make it a little bit harder to get like a grounding here. And so we're just going to assume that we're not doing much with solvents, and then if it pops up on the test, I'll give you a heads up. So really quick, a little quick class just here. In your head, not out loud. Not out loud. I want you to be an investigative journalist. You're touching the earth and saying, something happened here. What happened? I want you to look at this. I want you to try to find pieces of evidence for this being SN2 versus SN1. So take a minute, examine the evidence, and think, and then I'll ask, does anyone have any evidence to present? So take a second. SN1 versus SN2. What do we think happened? Order, order. I will now hear evidence on the trial of this reaction. Who has evidence to bring? Yeah.
I said that because it was, well, in my head I said that because it was a secondary halide, that it would be SN2 because then both of them would be fair for SN2 and SN1, but then SN2 would be priority.
Heard. That is doing a little bit too much interpretation for me. I like it, but let's think about more concrete evidence before we state our conclusion. So what's a piece of evidence?
Well, I was gonna say that the plus or minus indicates a mixture of SN1 and
That's some evidence. We have a racemic mixture. So this is indicating probably SN1 because we get mixture of stereochemistry, right? Whereas SN2, we're always going to have inversion. We're going to get one product. Okay, so that's one piece of evidence in favor of SN1. More evidence?
I was gonna say like the same thing. Like there's no inversion of stereochemistry.
Work. Other piece of evidence. Yeah.
That there's the benzyl rings, so they make for a good carb.
Ding dong! Ding dong! So we have the benzylic position. This carbocation is stabilized by a bunch of resonance. So if we have a really, really stable carbocation, it's giving SN1.
That's what.
There is a third piece of evidence. Does anyone see the third piece of evidence? Yeah.
Is it kind of bulky?
It's not exactly about the bulky, because bulkiness of the like electrophile we don't care for as much. Like it's much more when it's a bulky nucleophile that's kind of the issue. But it does have to do with the nucleophile.
Is it because it can be the H bonds that it's not favorable for the SN2?
Not quite.
Versus
Is it 'cause
Naomi.
it's not opposite?
Yeah.
So tell me about home versus Naomi.
So Naomi, like the oxygen is more negative than that.
And so that makes it a what type of
Better
nucleophile?
negative.
Good nucleophile, strong base.
Yeah.
But alcohol over here, poor nucleophile. So because we'd have a bad nucleophile, that's going to make it less likely to do SN2. So, thank you for coming. The jury has now decided. I have the verdict. We're going to say it's SN1. Here we are. So, okay. Now that we've kind of done a trip around the world, talked about all four kind of major reaction types, let's put it together into this GFP system. So GFP is kind of an algorithm for thinking through all of the different possibilities. And generally speaking, for each type of reaction, there is one major thing that you should associate it with for how favorable. So for SN2, it's sterics. For E2, it's base. And for SN1 and E1, it's carbocation stability. This is where I was trying to do like SN2 sterics, SN2 sterics, E2 base, E2 base, 1 carbocation, 1 like. But it's a bit much. Like again, like. Hey, I did not expect the enantiomers to actually happen this year. Like. I workshopped that with ChatGPT last year. Like I went through it. But yeah, so these need to be the number one things that come to your mind when you're playing this game of GFP ranking. These are our main rules, and then we have some addendums that we need to cover. But so SN2 sterics, if the electrophile is methyl or primary, we say it's good. If the electrophile is secondary, we say it's fair. If it's tertiary, we say it's poor. And also if our nucleophile is bulky. So this is again where it's about more the nucleophile bulk. So if our nucleophile is bulky, then it goes into the poor. Now E2, it's about base strength. So OH minus or better, that's like OR minus 2, good. H2 or weaker is poor, anything in the middle is fair. Then for SN1, E1, it's about carbocations, tertiary or better, resonance, which is a lie. Those are good. Secondary is going to be fair, and primary methyl is going to be poor. Now, this is going to be our basis, but we need to add in a few things so we don't get tricked. So 1, we need a nucleophile vibe check of is our nucleophile bad? If it's not a good nucleophile, it can knock it down a little bit, maybe from like good to good minus or good to fair, something like that. It's kind of semantics, what the details you want to do, but it's just something that we have to think about. Another one is the E2 reality check. Is there a beta hydrogen? Is it possible? Can it be anti-periplanar? And then in this system, we're doing a lot of generalization. So we're very often going to have ties in our GFP rankings. So when we have a tie, whatever is kinetically faster wins. So SN2 is faster than E2, is faster than SN1, is faster than E1. And that's for our kind of tiebreaker. Now, I have some like fine print things that you'll see as you kind of work through things. I also made this page, which it's a little ugly. Again, I didn't have enough time to like format it to make it like look fully ossified. This is a half ossification, if you will, a botched ossification. But this page I used to call what to expect when you're expecting substitution elimination problems, because these are all of the ways that we can try to trick you. So it's like our beta hydrogens existed. The Hoffman versus Zaitsev for multiple beta hydrogens. Each you on a ring. Some benzylic things like nucleophilicity, basicity. I talk about like alcohols, alkoxides, all of it. I just try to have like one reference sheet because there's not really going to be like a reaction summary thing because it's just 4 reactions and that's not the hard part. So this is my kind of review sheet for this lecture. But let's do a couple together to get you started, and then I'm going to give you like 10 to 15 minutes to work through a bunch of them. So, first one, we start off ranking it for SN2. So, SN2, what do we care about? Sterics. So, we look at our electrophile. Is it primary, secondary, or tertiary? Primary. So, is it good, fair, or poor?
It's so good.
Good. Now, we have to do our nucleophile vibe check. Is this a good nucleophile?
Yes.
Yeah. So, we stick with good. Yeah, Naomi. Yeah. Then, E2, we are looking at what?
We're looking at the base.
The base. So, our base here is OME minus. Is it good, fair, or poor? Good. It's like OH minus. So it's similar. So it's a strong base. So it's good. And we have beta hydrogens, right? Reality check. Yeah. Then last one, SN1E1. Okay. Well, if we formed a carbocation here, it would be a primary carbocation. Good, fair, or poor? Poor. So we have a tie. Good and good. Who wins between SN2 and E2? SN2. So that is the major reaction that happens, and we can draw our product. OME comes and does the substitution. Let's do one more before I turn it over. So let's look at 6D here. So is this, for SN2, primary, secondary, or tertiary? Secondary, right? And it's not an alkyl halide, it's this tosyl leaving group, but same idea applies here. So this is secondary. So do we think good, fair, or poor? Fair. We have like a meh nucleophile though, so our vibe check. So I might give her like a fair minus, but like, then E2, we're looking at base strength. So this is an alcohol or alkoxide? Alcohol. So good, fair, or poor? Poor base. High poor. Then SN1E1, we're looking at carbocation stability. We would have a secondary carbocation, so good, fair, or poor? Secondary is fair. Yeah. So we have kind of a tie here between these two fairs, and this is kind of a weird situation of like nuance. Like where you are tied fair for SN2 versus SN1, that's where things like solvent can come into effect. But here, I know I put a little minus. I would still say probably SN2 is going to be the major one. And again, this is where it like breaks down a little bit, this system. It's not perfect, but it's better than not having a system and then just kind of like going through the question, trying to figure it out. So generally speaking, if these are both fairs, the winner is going to be the faster one, the SN2.
Even if it's a fair minus.
Yeah, and again, that's why this like minus holds less weight.
Yeah.
And this is an oversimplified system. You could have fair, and like you could alter various conditions and choose one or the other. Other classes will go into much more detail with that. We do not as much. So now, for the substitution, what do I actually place here? Do I place an OH or an OET? You place an OET. And that's because it's way easier to break an OH bond, like acid-base stuff, than it is to break an O carbon bond. So that's another common mistake I see. So I'm going to let y'all work through this for like, I don't know, 10 to 12 minutes. This is pages 5 through 7 in the PSET. And then page 7 is going to be a little bit more complicated, so try it out. And then I will circulate and answer some questions.